have direct and inverse variations. That's the two types. And what you do is you let K be some real number. Now, initially, you do not know what K is. Okay. Y varies directly as X. Y is directly proportional X are equivalent statements. Okay, we're just talking language so far. This is all we're doing so far. Here's the general equation for what we call a direct variation. Y equals Kx. Now, the important thing to know about this, when it is direct variation, if you replace the original X with a bigger X, like the first time it was 5, next time it's 10. Y will also increase. If you replace X with a smaller X, then Y likewise will proportionally get smaller. Okay, and that's where that word proportional comes into this. Now let's talk about inverse variation, general form. Here are the two ways you could say that. And here is the general formula for that. In this case, if X were to be replaced with a bigger X, okay, in this case, X or Y rather would go down. It would get smaller. Inverse, the opposite. Okay. And likewise, if X were to decrease or get smaller, go from 5 to 1, Y would increase. Now, why would that be? Why would that be? Well, let's say this is 10. No, let's say this is 20. And this is 10. 10 goes into 22 times, right? So the answer for Y would be 2. Let's say that we increase, well, I didn't pick a good example. Let's use 40 and 10. 40 for K. If this is N, then you would have 4. If we increase X to 10, we started with 10. If we increase X to 20, then our answer divided into 40 would be 2. So if this gets bigger, that gets smaller. Likewise, if this gets smaller, if we decrease X from 10 to 5, then instead of 4, we would get 8 when we divided 5 into 40. So that's how this one works. Now, you've used this before in D equals RT. And R most likely would have been the K term. Or it could have been T. If you knew D and R and you didn't know T. Or if you didn't know T and you did know D and R. I think I just said the same thing twice. But anyway, this is a direct variation. Now, when we solve, in this case, for T, if we want T, it would be equal to D over R. This would be, if it's 500 miles to Denver, my constant term, and I go 60 miles an hour, how long would it take me? If I go faster, it's going to take me less time. If I go slower, it's going to take me more time. that fits this pattern. Here, this one just says, how far can I go if I drive this fast for that long? If I drive faster, then it'll take me farther. If I drive slower, it will take me shorter. And so that fits this pattern. And that's kind of how these things work. In this case, the K is the constant of variation. Now, the general process when we get one of these equations is the first thing we have to do is solve for K. Then we rewrite the equation, which is called the equation of variation, using that discovered K value. And then they'll give us a different X to solve for. So let me erase these marks. And we just simply want to write these. That's all we're doing right now. Well, that one is that. X, notice this time they swapped around my X and Y variables. Be careful about that. They probably will do that on the final. Okay. But you still work them the same way, except you're solving for X instead of solving for Y. This one, Z varies inversely. That means K over whatever the X term is. This time it says the cube of X. So that would be your general formula. T varies directly. This word varies is where your equal sign is going to go. T varies directly as W and inversely as Q. Now, this one has both direct and inverse variation in the same problem. This one looks like this. The KW is the direct part of it. The K over Q is the inverse part of it. Okay, a circle's area, A equal pi r squared. Normally we think, right? A circle's area varies directly as the square of its radius r. Well, in this case, pi, 3.14, is the K value. An electrical resistance of a wire varies directly as its length L and inversely as the square of its diameter D. That's actually kind of an important formula. Grab one of those handouts too, and you'll need to fill it out and turn it in before you leave this morning. Okay, now, what this refers to, there are two things that you become concerned with on wire. Okay, now the two things that you become concerned with are its length and its diameter. Okay, now what this says, the electrical resistance, that means heat. When you put an electric current into a wire, it heats up. That's how a radiant heater works. That's how a griddle works. That's how a stove burner works. You put so much current into this thing, and then depending on its diameter and its length, will say how much it heats up. and we call that resistance. Okay, where does this affect you? Extension cords. This weekend, when I did that dinner for my grandchildren's swim team, I had to have 3 different extension cords for crock pots, an oven roaster, and a griddle. Now, the oven roaster and the griddle take quite a bit of energy. They get pretty hot. The crock pot, not so much. For the crock pot, I could use what's called a 16 gauge wire, which is a typical extension cord that you'll find at Walmart or someplace. Now, for the roaster and for the griddle, I needed to use a minimum of a 14 gauge, if not a 12 gauge extension cord, because pull more current, and I don't want to blow a circuit breaker by overheating or cause a fire by overheating something. Okay, that's why they tell you don't hook extension cords into each other also, because that increases the length. And what this formula right here says is the longer the wire divided by the square of the diameter of the wire determines how hot that wire is going to get. Okay, that's what that formula is telling us. And wouldn't that have to happen now? That R equals K L over D squared. Okay, so the diameter of this wire squared divided by the length times this K value, and a little later we'll deal with that, is going to tell you how hot this wire gets. Now, when I put an inverter in my camper, that means I change battery power to AC plug into the wall power. It was 8 feet between the inverter and where my battery source is. Now, the inverter I've got runs on 1500 watts to 3000 watts, so I can run a lot of stuff with it. Okay, typical light bulb, 100 watts. Okay, that projector, probably about 300 watts. My griddle, 1200 watts. A microwave, the typical ones you buy anymore are 1100 watt microwaves. They're the good ones that heat fast. So I had to get wire about this big around. It's called dot size double aught. Now, I mentioned 14 and 16. 16 is smaller than 14. 18 is smaller than 16. 12 is bigger than 14. Double aught is 8 times bigger than 12. The double aught is actually about this real diameter wire that I had to use, so that I didn't potentially cause a fire by it overheating. Okay, now that's what this formula is about. For those of you who are going into engineering or anything where you need to deal with electricity, in your handout packet is a whole page of nothing but electrical formulas for you, just as a resource. Okay, what if you want to switch over something to LEDs? You're going to have to put some resistors in there, things that drop the voltage down to acceptable levels, voltage and amperage. Okay, well, these formulas work for that too. And I've shown you my model trains in other lessons before. And when I put in the lighting systems for them, I had to drop 20 volts to 5 volts. And so that's just one little usage that I've had for that. But at any rate, that's what this is about. Okay, circumference of a circle. Circumference of a circle varies directly as the radius. Well, there are 2 formulas for the circumference of a circle, if you recall. Pi times the diameter, and also pi times 2 times the radius. Well, the diameter and 2 times the radius are the same thing. Okay. Now, they're saying this. So, V equals something times R. Well, in this case, it would be pi times 2, or 6.28. Okay. At a constant temperature, the volume of a gas varies inversely as the pressure. V is my variable. Varies inversely as P, my other variable. Okay, so there is my general formula. And then they would give us some numbers for V and P so we could figure out K. And then once we K, they'd give a different pressure and we'd have to figure out a new volume. What the heck is this thing talking about? Ever seen a balloon that's filled? What happens if you put it in direct heat sunlight? The pressure increases, the volume of the balloon increases until finally it bursts, right? What happens if you take that same balloon and put it in a cold refrigerator, a walk-in refrigerator? It's going to shrink down. The volume will decrease. That's what this formula is about. You know what? That also applies to the efficiency of the propane in my camper. In cold weather, it doesn't go as far. Okay? I use it up faster. So that's what this formula would tell us. Now, as the pressure increased due to the heat of the sun, okay? Now, let's go on. Length of time for a meeting is directly proportional to the square of the number of people present. That one's kind of a joke one. What it's saying, the more people you got in a meeting, the longer the speakers talk. That reminds me of a couple of preachers I've sat through. Okay. Let T be the time. Okay, well, they're just playing the game on this one. Like I said, that one's kind of a fictitious one. What about this one? The time T it takes to drive a particular distance is inversely proportional to the speed S. Okay, we've got distance and we've got speed, which is the same thing as rate. And we've got time. This is a D equal RT problem, basically. Okay, the time it takes. That's this variation right here. T equals D over R, or in their case, S, which we've already talked about. The amount of your paycheck, if you work somewhere. I don't know about you guys, but I had to have a part-time job when I was in college until my junior and senior year, when I had a ROTC scholarship. And actually, I still had to have a job then because by my senior year, I was already married and we needed money. The amount of your paycheck, P, varies directly either up or down, to the number of hours that you work at whatever pay rate you have. Okay? Let's put in $20 an hour. Back when I was in college, you were lucky if you got 5. Most of the time, it was more like 350 or 4. You work 10 hours times $20 an hour, you get 200. Okay? You work 20 hours times $20 an hour, you get 400. This is a direct variation. You take off some time and only work 5 hours, you only get $100 of pay. So your pay goes up depending on how many hours you're working, assuming your hourly rate is constant. Now, so far, all we've been doing is learning how to write general formulas. That's all we've been doing so far. Now we're going to start solving K. Okay, this is the stuff. What am I doing? Okay, here's one. Y, here's more translating into formulas. Y varies jointly. I haven't talked about joint. Joint just means you got multiple variables, and they can either be direct or inverse. But joint just means multiple variables is all that it means. You still have some constant value. Okay, so Y varies jointly as U and the square root of B. And then there, of course, is my K. Speaking of KU, I am so happy they beat OU this weekend. All right. Now, gravitational force between two planets varies jointly as the product of their masses and inversely as the square of the distance between them. A lot of verbiage there. What are they saying there? Well, they're going to let this be the mass of the first thing, this be the mass of the second thing. This is the mass of the Earth. This is the mass of the Moon. Okay? F is the gravitational force. And D represents the distance between them. Now, here's the Earth. I guess I should do that in blue. Now, the Moon, on the other hand, and I don't have anything gray, goes in an elliptical orbit around the Earth. Twice a day it's closer to the Earth. Twice a day it's farther from the Earth. Ever heard of something called high tide and low tide? That's what causes it. And this formula is what can record it. The gravitation, oh, I need to put the Moon in here somewhere. Okay. So as the Moon travels closer and farther, the amount of force that the gravitational force or mass of the Moon places on the Earth divided by the distance squared is what causes the high and low tides. Any of you ever been, when you went and buy a truck, and it feels like you're being sucked into it? The difference in the mass of that truck and the mass of your car, it has a greater mass than yours, and depending on how close you pass to each other, there actually is a slight sucking in towards each other. And then you reach the point where the air pressure then tries to push you apart. And you can usually feel that after you get past them. But that's what this formula is about. So this stuff we're doing right now has some real world applications, whether we think of it in mathematical terms or not. And there's the formula for that. And this, that K represents then, of course, the constant of gravity. Okay, here we go. Another statement, A varies jointly as B and C. What's the answer? What's the answer? Somebody speak up. A equals KBC. KBC equals KBC. This one, X varies directly as the square root of Y and inversely as Z. That one I can't speak. That one I got it right. X varies directly as the square root of Y and inversely as Z. Okay. Any questions how I got that? Okay, now applications of this. Write a general variation model that relates to these, like K represent the constant. Well, we've been doing a whole bunch of that. That's the first step, is write the general equation. That's what we've been doing so far. The second step, solve for K by substituting the known values of the variables. Okay. Third step then, substitute K into the original variation model from up here. In other words, you replace the K with the number. And that's called the equation of variation. And you will be expected to give that equation with the K value replaced as your final answer on some questions. And then on other questions, you'll have to go on and continue the problem and get the new values if I replace, for example, the X. Now, let's look at this. The variable Z varies directly as W. When W is 16, Z is 56. Okay, so first we're going to write the equation of variation, which is that. Okay, that much we've been doing. Now we're going to replace the Z and the W with the 56 and the 16. Okay. So we know this, we know that, we don't know K, we can find K. How are we going to do it? Divide both sides by 16. This would be the same problem as if we had 56 equals 3 or 16K. Just because it's behind it doesn't matter, the 16 being behind. And here you obviously would divide by 16. What do you do there too? Okay, so we do that. We divide both sides by 16. That side cancels out, leaving just K. This side, all you can do is reduce it. I suppose you could change it to a decimal with long division. But this is better. And what is that? 3.5 in reality. So, going to my next slide. Since we're replacing K with 7/2, then here's my equation of variation. Okay. Now, like I said, in some problems, this is all we're going to ultimately ask for. But in other problems, we're going to give you a new W value, and then you have to find a new Z value using this. We're not, okay, in this case, we're going to replace W with 84. So instead of W being 16, we're changing W to 84. Now, what is the new value of Z? This is the ultimate answer. Well, how are we going to get rid of, well, how are we going to find? Well, we're just going to multiply those two together. Okay. 2 goes into 84 42 times. 7 times 42 is 280 something. 294. I have to carry. Okay. Did you see how I did that? I did this reduction there, and then 7 times 84. 7 times 8 is 28, or the 42. 7 times 4 is 28, and then 7 times that's 14. So 28, and then 14 added on there. The 20 actually being 280. That's using distributive multiplication. Okay, now variable Q varies directly as the square of V. When V is 2, Q is 40. Okay, so Q varies directly as the square of V. That's my general formula. When V is 2, Q is 40. Okay, so you follow what I've done so far. This becomes 4. Divide those by 4. K equals 10. So my new equation of variation is Q equals 10V squared. Now, here I solve for the constant of variation. Now find Q when V is 7. So we're going to put 7 in here, like so. And we get 10 times 49. So Q equals 490. And that's the ultimate solving on this problem. Okay, so that's all the steps. What did we go to? First, we wrote the general equation. Then we solved for K. We wrote the equation of variation. And then we solved for a new variable. So that's the total process on this thing. Anyone not ready for me to erase yet? Speed of a racing canoe in still water varies directly as the square root of the length of the canoe. They're saying that how long a canoe is has something to do with the speed it can go in still water. Would that have application in sculling? Olympic canoe racing? Where they got 8 or 10 people in the boat? Yeah, it would make a difference. Okay? Might make a difference you going across the lake yourself. If a 16-foot canoe can go 6.2 in still water, find a variation model that relates to the canoe of its length. Okay? Well, let's let S represent speed. I'd rather use R for rate, but will you go with that? L for length, that's kind of obvious. And then we've got K. This is a direct variation problem. So we put the 16 in here, the 6.2 miles an hour. Square root of 16 is 4. Divide by 4. So my equation of variation is 1.55. Okay. Now, instead of 1.55, we could have done this and this. And so 62 over 40 reduced to 31 over 20. We could have used it as a fraction instead of a decimal, but in this case, probably a decimal is more efficient. There's my new equation of variation. What if you had a 25-foot canoe now? We had a 16 before, right? And it could go 6.2 miles an hour. So let's see what a 25 would do. Here's our constant of variation. We're going to put a 25 in there, square of. That's 5 times this, which is that. By the way, no, this is an exact value. So that speed would be 7.55, 7.75. In other words, changing from 16 to 25 would increase your ability to go by about 1.5 miles an hour faster, approximately. All right. This one could be practical to if you like the outdoors. We did some hiking this summer, my family. We went to a place called Devil's Lake up in Wisconsin. Beautiful lake, kind of a small lake. Probably no bigger than Lake Afton out by Goddard, except compared to Goddard, which is just flat prairie land. And this one had 300-foot bluffs. So we hiked up from level to the lake at the beach area to the top of the 300-foot bluffs. And we fortunately decided not to take our dogs with us. And but we got thirsty on this thing. Okay. And water replenishment is critically important to human survival. Well, in here, water needed by a hiker needs 2.4 liters. Just big around that much, 2.4 of those for a 3-hour hike. Now, we didn't have that much. We had 16 ounces times 2 bottles. 2 16-ounce bottles apiece, which roughly equals 1 liter. So we had about half the amount of water that we should have taken, is what this is saying. Now, write them off that relates to that and how much water would be needed for a 5-hour hike. Do I need to work this problem? Would you like it, or would you want to continue forward? Yea or nay? Yes? Okay. The amount of water needed, and this is in ounces, or excuse me, in liters. Okay. Equals K times the number of hours, right? 2.4 equals K times 3. Divide by 3, divide by 3. K equals 0.8. In other words, that means we need 0.8 of a liter, or about a 16-ounce bottle and a half per hour. in reality. So my constant of variation now is the water that we need equals 0.8 per hour. So in this case, we put in 5 hours. Well, 5/8 are 40, and put the decimal in the right place. So the amount of water we would need would be 4 liters of water. And don't forget the label on these word problems. It will cost you if you don't. 4 liters. Okay. So we basically had half what we needed. And very frankly, when we got back to our camper, I drank some water. Well, actually, I drank some pop. But they say it's not as important. Interesting. I read something interesting the other day that I had never heard before. You're cold, aren't you? So am I. If it makes you feel any better, this thing doesn't hold much heat. It's really an overshirt. I heard that milk, excuse me, will actually rehydrate you faster than water. I've only read that once. It's interesting though, if it's true. So I just share that with you for whatever it's worth. Okay, this one I also have a true experience with. The loudness of, whoops, I went back. The loudness of sound measured in decibels varies inversely as the square of the distance between the listener and the source of the sound. If the loudness is so much at a distance of 10 feet from a speaker, what is the decibel when you're 20 feet or twice as far away? True story. My wife and I went to a Trans-Siberian Orchestra concert. I think I've told you maybe this once before. I don't remember. The seats we got happened to be free seats we won in a radio test. And they were about as far as from here to that wall from this speaker bank that was as big as that wall. They had one on this side and one on the other side of the stage, about that big. And we were close. My wife, unfortunately, has almost total hearing loss in one ear and wears a hearing aid in that ear. Hearing aids only totally amplify sound. They don't discern it like your ears really do. Okay. The result is it was painful for her because they are loud. I love their music, but they are loud. But coming out of that concert, she was in physical pain to at some point as she went out into the concessions area outside the auditorium area to get away from such loudness. And I mean, we were sitting here like this the whole time. And now, what has this formula got to do with this? This says if we were farther back, it would have been more tolerable because the loudness of the sound would have been perceived as less. Okay, that's what this problem is about. Now, if you let L represent loudness, which represents decibels, and D represents how far you are from the source of your speakers. There's the formula. Okay. Looks a whole lot like that electrical resistance formula, doesn't it? Except we have diameter instead of distance. Well, because this is inversely, the farther we are, the less the sound. The closer we are, the more the sound. So anyway, we put in the numbers they give us. And we saw this time, first we changed this to 100. Now, instead of dividing both sides by 100, we're going to multiply both sides by 100. Those two cancel, and over here, I end up with getting that many decibels, and that is loud. Okay. Now, what is that's my constant. Well, that isn't the decibels, that's the constant. So anyway, here is the constant over the distance. So now we can put in our different value than 10. What if you were 20 instead of 10? Okay. Well, in this case, 20 squared is 400. And that number divided by 400 is 4.8 decibels. Actually, that's not very loud. And 7.8 is not very loud. My generator on my camper is about 50 decibels. Okay. When you listen through a set of headphones, because they are so close, we're actually in somewhere in the 75 to 100 decibel range. 100, you're starting into the damage your hearing range. Cautious with it, headphones. All right, here's another one. This one deals with investments. Okay, we're going to skip over that one for right now. Let's do some joint variation, multiple variables. Okay, this is just some. It's trivial information in reality, but it's just describing a real force. Okay, it really doesn't affect much. And this is true. Likewise, the tornado that went through my hometown on May 5th of 1960, now back validated as an F4 on the Fujita scale, which destroyed 80 homes, most of downtown, 5 churches, and killed 18 people, most of whom were on my paper route, because the town I grew up was between 2 hills, and the tornado came right down one hill and up the other one. And the people on the downhill side had 0 warning, because a hailstorm 30 minutes ago that had hail this big around had knocked out the town's power supply and warning system. Well, anyway, phone poles through the peaks of roofs, and literally straws stuck into telephone poles. And it was weird, but yet the last house hit on the top of what we call North Hill was a very modern one, a lot of glass. The roof went off, but on their dining room table, they still had teacups, china teacups sitting there undisturbed. Really weird. The post office downtown, a wall lifted up, and half of the guy's pair of pants were on one side of the wall and half were on the other side of the wall, and then came back down on it. But anyhow, back to this problem. Kinetic energy of an object, that means the force it's going to hit something with, varies jointly as the weight of the object and the square of its velocity, how fast it's going. In other words, the heavier it is, the faster it's going, the greater the kinetic energy. Does that make sense? That's why they use 300-pound tackles in pro football. When they hit somebody, it moves them. Okay, so here's just a problem. They're giving us the information. Oh, here we go. A 1/2-pound stone at 60 miles an hour. Now keep in mind, they could have as much as 100+ miles an hour wind. But this stone is flying at 60 miles an hour. It says it has 81 joules of kinetic energy, okay, of movable force. What if the wind speed doubles? E is the energy, W is the weight, V is the velocity. So we have three different variables, so we have joint variation. Okay, there's our formula. Here's the substitution. The arithmetic, 60 squared, just bring down the 0.5, multiply those two together, half of that is this. Now divide both sides by 1800, and you get, okay, actually could have reduced by 3 and that by 3, and had 27 over 600, then you could reduce by 3 again, and whatever, fractionally if you wanted to. So anyway, here's the formula. Now they're going to give us some information to put in here. Well, that's as far as they're taking this one. This one is actually very similar to the sound one. Remember how loud it was depended on how close you were. Well, in this case, is how bright is light. Right now, if I look at that projector, I see purple spots in my eyes. And I'm about 10 feet from it. If I got 20 feet, and right now only about 15, but if I got 20 feet, it wouldn't be nearly as bright. I could probably, I mean, it would still mess with my vision of seeing you guys, but it wouldn't just overwhelm me. Okay? And if I got 30 feet, finally, if I got far enough, it would just be a little point of light, kind of a star in the sky. You know, those stars are actually as bright as our sun. They're just farther away. So consequently, their brightness is less. And that's what this formula is about. Okay? Well, they tell us, here's the formula. Solve for K. We put in the 3 units for a 50 CV lamp. Most of the time, lamp brightness is registered in something called luminance. When you buy light bulbs, look for the luminance as well as the wattage. The wattage is how much electricity is used. The luminance is how bright it is. Okay? So that's a consumer thing. And then here's the distance. Well, you solve this. 50 over 100 is a half. And a half times, or half, so you take 2 over 1 times both of these, and you get K equals 6. Once you've got the 6, then you substitute it in with new data. 9 feet instead of 10 feet. And you get 2. So it made a pretty big difference in that case. Okay. Here's just another one of those. Actually, I think I must have gone backwards. Now, I want to do one before I do this. Any of you ever heard of this formula? You have. It's the atomic energy formula. Energy equals mass times a constant squared. Now, I'm going to tell you in this formula, the constant squared is 186,000 feet per second squared. That's the constant on that formula. Now, what does that mean? By the way, the speed of light I just quoted. Okay, that's the speed of light. Now, what this formula means is the mass of the atom that they're going to split with a force of the speed of light when they crack that atom. When they crack it, two things are going to happen. One, the mass is going to be slightly reduced. Okay? Because there are going to be some broken parts. And then there's going to be some heat. Ever seen the nuclear fireball and cloud? That's heat and pressure for the shock wave. That's the energy that gives off. Now, the closest equivalent I can give to you on that is if I have a board and with my saw, I cut that board into two pieces. When I get through, I take this piece of board and this piece of board that I have remaining, and I put them together, and they're less than what I originally had. Because I have 1/8 of an inch width of my saw blade that has destroyed that wood. Now, how does that destroyed part have, what form is it in? Well, part of it's sawdust, but also as that saw blade is going through that wood, it is creating frictional heat. So the energy from sawing that board dissipates part of the mass of the board given off, in this case, in sawdust and heat. Here, pressure, heat, and radioactive particles that are distributed when an atomic bomb goes off. Now, you may not have ever thought about this in terms of that formula, but that applies directly to what we're doing today. Okay? Now, let's get back to this. Here's a problem. A varies directly as B and inversely as C. If A is 20 when B is 4 and C is 5, then find B. First, you got to figure out the K from this stuff. Then you do this. You do it. You do it on a piece of scratch paper. By the way, you need one of those surveys to fill out before you leave. If you don't have any paper, you can do it on the back of that. You need a pencil? I don't have a pencil. Got that. A equals B over C. Hopefully all of you got that far. Substitute in the values for and solve for K. There's your substitution. Hopefully you got that. Anyone have problem on that one? Okay. Now, the easiest way to deal with this is take 5/4 times both sides. Like that. So you don't need to use your calculator. These will cancel, leaving K. And 4 goes into 25 times. 5 times 5 is 5 times 20 is 100. Divided by 4, if you want to do it that way. Either way, you get 25. For K. Now, what do we do next? We take this equation and replace K. Replace C with the new C. And the A with the new A. So now we can find out what B is. Multiply both sides by 20. Now divide both sides by 24. And as an alternative method, you could have reduced this to 4/5 and then taken 4 this, 4 this. 5 goes into 30. 6 times 4 times 6 is 24. Could have done that as an alternative method. Okay. Any questions on this one? And we are at the end of exam 3 material. I've got to cover a little bit for the sake of Alex of exam 4 material for the remainder of class. Okay. So